speaker is Figueroa-O'Farrill, and he's talking about the geometry of supersymmetric PP waves.
Where would you like to put that?
Just put on the light here will go amber. It'll start green and go amber in 22 minutes, 25, yeah.
Okay, thanks. Okay, well, thanks very much for the invitation. It's good to be south of the border. I'll be talking about some remarks on the geometry of supersymmetric PP waves. This is based on work that I've done in collaboration with these people here who need no introduction, George Papadopoulos, Matthias Blau, and Chris Hall. And it's based on some papers that have already appeared in the archive and some work in progress with George that we hope to finish soon. Okay, so try to motivate the inevitability in some sense of PP wave backgrounds. Let me make some remarks about maximal supersymmetry and PP waves. So let's start with, for example, 11-dimensional supergravity with field, symmetric, and the 4 form. In order to derive supersymmetric backgrounds with fermions equal to 0, one basically analyzes this connection that appears when you vary the gravitino and then set the gravitino equal to 0. This connection is a connection on a bundle of representations of the Clifford algebra, and it contains the spin connection bit and then this F-dependent algebraic term, so it's the 0th order bit to the connection. And maximal supersymmetry implies that this connection is flat. And if you analyze the conditions for flatness, you find two things. You find, first of all, that F has to be parallel with respect to the Levi-Civita connection, and decomposable, which means that it can be written as a wedge product of 4 one-forms. And the second thing you find is some identity that says what the Riemann tensor is in terms of the metric and this 4-form F. And the point is that this is an algebraic tensor. So when you put 1 and 2 together, since F is parallel and so is G, then you find that the Riemann tensor is parallel, so you find that this is a locally symmetric space. Another thing you find is that by taking the trace of this, several traces of this second identity, you derive a relationship between the scalar curvature of the metric and the norm of the 4 form. So essentially there's two cases to consider. You can either have non-zero scalar curvature or 0 scalar curvature. In the non-zero case, you basically derive the Freund-Rubin ansatz. Basically, you decompose the space into a 4-dimensional bit and a 7-dimensional bit. And with a bit more work, by analyzing the actual equations, you do find that the two solutions that you get are the ADS4 cross S7 and ADS7 cross S4. If the scalar curvature is equal to 0, then there's two cases. Either F is 0, in which case you get the flat background, or F is null, and by analyzing the equations, you find that this gives rise to what I'm calling here a CWPP wave. And this had actually been discovered by Kowalski-Glickman in '84. When we set out to do this, George and I, we actually didn't know this solution, and our hope is in fact to show that there was nothing else but the anti-de Sitter solutions. So you could say that ignorance is bliss in this case. So the reason I call this CW, well, this is based on a theorem by Kain-Wallach in the late 60s, which classifies the Lorentzian symmetric spaces, at least in dimension higher than or equal to 3. This is not a trivial problem in the sense that in Lorentzian signature, unlike Riemannian case, it's not enough to look at irreducible actions of the holonomy group on the space. You have to make sure that if the holonomy reduces the space, actually you want to be able to decompose it as a product. So it's not a question of irreducibility of the representation, but rather of indecomposability. Namely, the irreducible factors should inherit the metric. So that's a little bit more complicated, but nevertheless, for the Lorentzian case, and this is definitely not the case for the other signatures, but for Lorentzian case, there is a classification theorem, and basically it says that there's 3 cases. So there's the anti-de Sitter and de Sitter spacetimes, and then there's a family of PP waves, which we call them CW in honor of Kain and Wallach. So one way to describe this PP waves is as follows. It's going to be a symmetric space, so it's some homogeneous space G mod K. It depends on some data which is encoded in a symmetric, so if it's in D dimensions, this is encoded in a symmetric matrix in the transverse space to the wave. So it's D minus 2 by D minus 2 symmetric matrix. The Lie algebra of the group G has generators, let's say EI, EI star, E plus and E minus, where I runs through the transverse dimension, so 1 to D minus 2. And this is basically the Lie brackets. The Jacobi identity is satisfied by virtue of A being symmetric. And one thing you can show immediately is that this is in fact a solvable Lie algebra, which is perhaps surprising. we can split the Lie algebra into a subalgebra K, which is the subalgebra spanned by the EI stars, and a complementary space, which is spanned by EI, A plus, and E minus. And, well, one K is actually a billion. So you find that what you have is a symmetric split. P is a representation of K, and then the bracket of two elements in P goes back to K. So you can give P the structure of a Lorentzian vector space by defining a K-invariant metric in the obvious way. So it's the Euclidean metric in EI, EJ. And then E plus E minus just has metric 1. So it's the natural. I mean, the notation is suggestive on purpose. And then just by general arguments, it follows that GK with the metric induced by this bilinear form is actually a Lorentzian symmetric space. And in decomposability, the fact that it cannot be written as a product of two spaces is basically equivalent to the non-degeneracy of the symmetric matrix. And in some natural coordinates, xi and x plus minus adapted to the basis I chose for the subspace P, then what you get is this PP wave metric. So comparing to Juan's talk earlier, my minus and pluses have been, they're changed. So my minus is his plus. The important thing to notice here is that this matrix here is constant. And it's the thing that appears in the structure of the Lie algebra. Okay, to actually get a supergravity solution, one has to supplement this for an ansatz for the forms which appear in the theory. So for example, for the 11-dimensional form, 11-dimensional supergravity, you have a 4 form. So the form is going to be null. So it's of the form dx minus wedge c, where c is some covariantly constant, which in this case really means, relative to these coordinates, really means constant 3 form in the transverse space, which is 9-dimensional. Or for example, in type 2b, one can turn on the self-dual 5 form, in which case you get dx minus wedge, a self-dual 4 form in the transverse dimensions. The symmetries of the solution, well, the isometries of the metric, you obviously have this group G. Remember, the space is of the form G mod K, so definitely you have an isometry group G. But then there is also some accidental, depending on what the matrix A was, there is some accidental symmetry, which is just the subgroup of SOD, which preserves that matrix. However, in order to have symmetries of the supergravity solution, you have to, of course, also demand that F be invariant. So what you have generically is going to be this same group G, and then extended by the intersection, but the rotations in the transverse space, which preserve both A and F. And by F, I mean, of course, either C or B here in these cases. Or there's also lower dimensional supergravities you can consider. Okay, so these PP wave solutions, they form natural ansatz to describe supergravity solutions preserving a fraction of more than at least one half supersymmetry. So several examples are the Kowalski-Glickman solution of D equals 11, in which the matrix takes this form. It breaks up into two, so it's block diagonal with a 3-dimensional and a 16-dimensional block, and the eigenvalues are basically 1/4 of each other. And C appears here. And this has symmetries. Well, you have an SO3 and an SO6, which act in each block. So the symmetry is a 38-dimensional group, which is G, semidirect product SO3, SO6. For the 2B PP wave, you find that in this case, A is actually proportional to the identity matrix, which means that the space-time is conformally flat. And B is some self-dual form, which breaks up naturally into volume form in a 4-dimensional space and volume form in the complement. And the symmetries are, again, now you find, well, at least locally, it looks like an SO4 cross SO4 extending the group G, and this has dimension 30. Okay, so there's other PP waves that people have found with more than 1/2 and less than maximal supersymmetry. There's a paper by these people discovering quite a big family of them, basically following these ansatz. And if you go to lower dimensions, there's also been some other maximally supersymmetric PP waves, again with the same ansatz. So let me make some comments about some similarities between these maximally supersymmetric solutions. Well, okay, I'll keep it here. So if we start with the d equals 11, so maximally supersymmetric solutions, forgetting the flat solution for a moment, we have the two anti-de Sitter cross spheres and this the Kowalski-Glickman solution. The thing they have in common, first of all, is that they're all Lorentzian symmetric spaces. And another coincidence, which now we understand, but at the time seemed a bit puzzling, was the fact that the dimension of the symmetry groups actually agrees. All the symmetry groups of these solutions are 38-dimensional. In fact, closer inspection shows that the isometry algebra of the PP wave is actually a contraction of the isometry algebras of the other two solutions. And this suggests the notion of a limit. For the 2B PP wave, one also, apart from the fact that, again, they're Lorentzian and the dimension of the isometry groups coincide, you find that they're, in fact, both conformally flat. Another similarity between the solutions is that they all admit isometric embeddings in flat spaces two dimension higher, so in signature 2D. And basically, not just the maximally supersymmetric waves, but in fact the generic PP wave with that ansatz admits an embedding as the intersection of two quadrics. Here I've chosen coordinates in R2D in which U1, V1, U2, V2 are null coordinates, so they're light cone coordinates, and Xi is transverse to that. And in which case, what you have is you have a circle essentially in a totally null plane, and then you have another quadric. And this can be, in fact, be explained. There's again ADS cross S, as you well know, it's again embeds as an intersection of two quadrics, and there's a way to relate this to embeddings, but I probably won't have time to go into that. Okay, so the way this coincidence can be explained is through the Penrose-Guven limit. I'll explain very briefly. So this starts by, well, you consider any Lorentzian manifold and you have a null geodesic, and then you can choose coordinates adapted to that null geodesic. Let's call them u, v, and yi. U is the affine parameter along the geodesic, so the geodesic vector is going to be ddu. And then v and yi, what they do is they label a geodesic congruence which has to be twist-free. Namely, the one-form dual to the geodesic vector, to ddu, is, in this case, dv, it's closed. In this case, well, it's locally exact. So if you do that, you can choose coordinates in which the metric takes this form. Here, alpha, beta I, and Cij are arbitrary functions of your manifold, or your space-time manifold. But the important thing to notice is that there are some terms which are missing. For example, there's no du, dy term, and there's no du squared term. So now what you do in order to define this limit is you make a boost in the uv plane, and then you rescale the coordinates, the transverse coordinates. So you can introduce new coordinates, little u, little v, and little yi, and relate them to the original coordinates in this way, where omega is some, let's say, positive real number. And the idea now is to take the limit as this number goes to 0 while rescaling the metric appropriately. So you define a limit metric, which is taking the limit as omega goes to 0 of the metric simply taken in this, take this metric here, substitute this change of variables, it will develop some omega dependence, but because of the fact that precisely the du squared and the du dy terms are missing, there will be at least an omega squared out. So when you divide by omega squared, this limit is well defined. And by changing coordinates, I won't mention the change of coordinates, but essentially going from Rosen to harmonic coordinates or Brinkman coordinates, you can find a metric in this form. The difference from the CW metric that we had before is the fact that what you get here is a quadratic form in the transverse space, which is x minus dependent. Whereas in the case of the symmetric space, this is actually a constant. Well, this was known to Penrose a long time ago. Guven noticed that this also worked for supergravity theories. And in that case, what you do is you exploit the gauge invariance of the supergravity theory to choose a good gauge for the p-form potentials. So you choose a gauge in which the potential has no du component. So the contraction of ddu with the potential is equal to 0. And then if you do that, you can define a limit for the field strengths. Notice that the field strength is a p plus 1 form, but omega here is omega to the minus p. And I didn't write down, somebody left something here. So, excuse me. This then looks like dx minus wedge some form, which now depends on x minus. This is a form in the transverse space, so this is some p form in d minus 2, let's say. Okay. So there's some basic facts about these limiting objects. The first one is that they obey the supergravity equations of motion, provided that the initial fields, G and F and whatever else I have, does as well. And the reason for this is that this limit involves, in a crucial way, the invariances of the equations of motion of the supergravity theory. The invariance under diffeomorphisms, by choosing the coordinates adapted to the null geodesic, the invariance under gauge transformations in order to choose that gauge, and also the scaling symmetry, not of the action, but of the equations of motion, in order to, this rescaling, so omega minus p or omega minus 2 in case of the metric. This actually fits in very nicely with a formalism developed by Garroch about 3 decades ago in a paper called Limits of Space-Times. And using Garroch's formalism and extending it a little bit for this context, one can derive a host of useful consequences, which I'll list, I think. Okay. So essentially it comes down to listing some properties which the limiting solution inherits from the one you started out from. So the first thing that gets inherited are curvature equations. So any equation like, for example, the Weyl tensor equal to 0 or Riemann being covariantly constant, these things are inherited. So if you start with a solution which is, say, locally symmetric, then so will be the limit. If it's conformally flat, so will be the limit. If the initial solution was Einstein, then the limit was actually be Ricci flat. So it again remains within the class of Einstein spaces. Other things that get inherited are things like isometries, conformal isometries, and supersymmetries. And the way to realize this essentially is to exhibit isometries, so killing vectors, conformal killing vectors, and killing spinors of the supergravity theory as parallel sections of some bundle with connection. And I won't go into the details. It's in our paper if you want to read them. One very important property of this Penrose given limit is what we call the covariance property. And this covariance property says the following. The limit actually depends on the null geodesic that you choose. However, if two null geodesics are related by an isometry, then the Penrose given limits of these spacetimes will actually be isometric. So this is quite useful if you want to classify the different Penrose limits that you can have in a solution, especially if you have enough symmetry. So let me just review this very quickly. So at least locally, this null geodesic is going to be determined from two things. First, you have to specify the point at which you start the geodesic, say gamma at time, the affine parameter equal to 0. And you have to say in which direction you're moving. And that's just going to be a null direction in the tangent space at P. And P being the initial point of the geodesic. And the null direction is essentially a celestial sphere at that point. So the different Penrose given limits, once you take this covariance property into account, they're in one-to-one correspondence with the orbits of the isometry group of the spacetime on this bundle of null directions, which I call the celestial sphere bundle. So one example that's very easy to do is, for example, the case of an ADS space across a sphere. The space is homogeneous, so you can basically use the invariance on the isometry group to put your initial point anywhere you want. And now what you have to ask is, what is the, once you have fixed this point, what is the, what are the orbits of the isotropy of that point on the celestial sphere? And for this case, you find that there's basically two orbits. There's the big orbit, which is generic, which when you take the limit gives rise to the CWPP wave. And there is a small orbit which consists of those null directions whose component along the sphere vanishes. And in that case, then you get a flat space. So this allows you to say that there's only two Penrose given limits of spaces of the form ADS cross S. You either get a PP wave or you get the flat space, which is consistent with the fact that, for example, in 11 dimensions, we know that there's no other maximally supersymmetric solution aside from the anti-de Sitter solutions except for these two. because the fact that supersymmetry is preserved, taking any other Penrose limit of ADS cross S would give you a would give you maximally supersymmetric solution. But it's not there. So I'm actually going to finish a bit early. Okay. You can apply this to other kinds of solutions, provided you have enough symmetry to make some sort of argument about the orbits of the isometry group on this bundle of the celestial sphere. And we've done that for many different kinds of brane solutions in this longer paper. And another comment that I wanted to make, which I won't have time to go into, I could have, is the fact that one can generalize this Penrose-Guven limit for space-times with the signature, so multi-time, so signature 2n or 3, whatever. Essentially here, what happens is that the role of the null geodesic is now played by a totally geodesic plane. And in fact, you can use this to relate the embeddings of the anti-de Sitter solutions and the PP waves. In some sense, there is a 2-time Penrose-Guven limit which induces the standard Penrose-Guven limit of the embedded submanifold. Okay, I think I'll conclude here.
Are there any questions?
What is the celestial?
Hermann Nicolai from Golm, Germany. What is a celestial sphere?
It's the null directions at a point. So you look in the sky and the null directions of the null geodesics. And
Go outside and look up.
yeah.
Any other questions? Okay, go.
And which can I give a CW spaces?
Right, so the question is which of these CW spaces is conformal to which of these CW spaces? And the answer is I haven't thought about that, so I don't know if you know.
Any other questions? Okay.
The letters are fully open, I'm sure you're fresh air.